Hi everyone. So now let's talk about Bender's decomposition, which is an alternative decomposition framework to that we've seen in the last video. So now Bender's decomposition is also targeted to solve large scale optimization problem. Just like in a very similar fashion to Dantzig-Wolfe decomposition, it's also looking into solving several smaller scale problems successively. And just like any other decomposition method, it strongly relies on being able to identify what is a suitable structure to employ decomposition. One interesting thing about Bender's decomposition, and that's why I wanted to bring it up here, is that not only it permade several fields of where optimization has made quite important progress, is that Bender's decomposition is available in Cplex, which is a commercial solver offered by IBM that has been out for a long while and is probably one of the leading in terms of performance. So they do offer a built-in version of Bender's code since version 12.7 that you can use, configure to your own use. But to exploit the most benefit of it, you have to be able to tell how it should employ Bender's decomposition. And that can make a big difference in terms of the quality of solution performance you're getting. So let's have a look at what it is. So we once again are defining our problem like so. So we have this structure that we have these variable x's and these variable y's, and you can see that these variable x's, the x variables, they are playing this role of being complicating variables. Complicating in the sense that they appear not only in this set of constraints, but they also appear in this set of constraints. So this column associated with the variables x. You can see that if it weren't for the variables x, this problem would be separable in the dimension k. And that's what I am highlighting in blue here. There you go. So we're consistent. So you can see that if it weren't for this variable x, you could solve these problems in case over and over, separately, one per processor over and over, just by changing the data for that specific k and solving again. So you can see that P, that's this structure that we call, in the context of Bender decomposition, you might see this word or this term, block angular. Block angular means it's something that you take from matrices. It means that when you look at the matrix associated with this problem, you see that you have these blocks of coefficients that can be arranged in a diagonal shape, and that's kind of like the reason why you have this name block angular. But that is not fully exploitable as yet, because if it were, you could simply separate these into these subproblems and solve them. But turns out that you have this big column that is cutting across all the subproblems. So the subproblem 1, subproblem 2, subproblem 1 has its subproblem 2 has its subproblem. So each subproblem, 1, 2, 3, all the way to k, they are all connected to this variable x, meaning that you can't solve them separately because you need to know what is the value of the solution x in each of the subproblems. All right. But one interesting aspect that arises here is that if you were to fix the variable x to, say, x bar, so the problem then becomes separable, because what you can do is, as soon as you have a value for these variables x, this becomes a constant that you can just send to the other side here and say that, say, this is E1 minus C1 x bar. This is minus C2 x bar. So, and this is just a right-hand side because this is a constant once you know the value of x. So your subproblems, they can be written like so, that you have a problem for each k where you're just optimizing y, and this is a right hand side a constant. And sometimes these cannot, definitely not sometimes, but definitely these can be solved in parallel if you have the machinery to do so. But most interesting is that sometimes these decompositions are such that when you look at the subproblem like this, it has like a very nice structure that you can exploit. It can end up being, say, like a knapsack problem or some sort of generalized assignment problem for which you can find efficient heuristics to solve. Or even can have something that, you can find a closed form solution to it. So that is beneficial in that. The tricky part in this is that this fixing cannot be made arbitrarily, right? You can't really, unless you have some sort of feedback process, just by solving, finding a value for x, fixing and solving the other subproblems, you're not finding optimal solution. You're finding what is the optimal response for that decision x, but not necessarily that is the optimal decision x. So this process of fixing the solution is not sufficient. But we can use that in our favor. So in order to derive better decomposition, so let's assume that we have this value z of xk, and here I'm on purpose making the explicit that depends on the variable x. So if you plug x bar here, then you plug x bar here, and then you solve sk, then you obtain zk of x bar. So that's what that means. And we will have this outstanding assumption. We have that we're minimizing, so if you have positive infinity, then it's infeasible, but if it's negative infinity, then it's unbounded. Okay. And once that is set, we can see that our original problem P, that I'm calling here PR as in reformulated, can have this form that is a bilevel problem. Bilevel because just like in Inception, the movie, you have a minimization within a minimization. So it's the minimization of this z and that z, the evaluating z for x, which is coming out from this, say, outer problem, entails actually solving another problem. And you notice that we're doing like a reverse step of what we would do, because, well, since this is a minimization depends on x, there's no reason why you can just go and minimization, just plug this thing here and end up with the original problem we're trying to solve. But we're trying to expose a separable structure in this. Okay. So it means that then once we have this sort of bilevel structure, obtaining this term requires solving sk, which in turn depends on x, right? So the way to deal with that is that we can use duality. And by using duality, what we're going to try to do is to get an implicit representation for this, which would in turn make this formulation for PR tractable. Okay, and now you should be suspecting that whenever we're talking about implicit representation, we're going to one way or another invoke something like the representation theorem. But here it is. If we go about and write the dual formulation for sk, represented here by S capital D for subproblem K, it looks like this. And this is, once again, I advise you to pause the video here, look at the formulation of the primal, which is in the previous slide, is this, and see how that is indeed the actual dual for the subproblem. And you see that this is the new dual variable P. So let's call, and once again, notice that x here now is in the objective function, while before it was part of the constraint set. Okay. So let's call PK this feasibility set here, which is basically the feasibility condition for the dual subproblem. And let's assume that this is not empty. So we're talking about interesting problems here with at least one extreme point. So we don't want then any of those to be infeasible, because that would mean that the whole problem collapses to being feasible and is pretty trivial. So we want something more interesting than that. And look at what we're going to do again. Once again, I'm going to call the representation theorem, this time to make a representation of this PK. So bear with me now, because the indices start to get a bit messy here. So PIK is the collection of extreme points for subproblem K, and I have I of them, so they are indexed by I. So I have capital IK of extreme points for that subproblem K, and I have capital J extreme arrays for that subproblem K, each of them with this index low k as J, and represented by W, like we've been doing. Okay, so these are the extreme points and the extreme arrays of the dual subproblem. Okay. All right. So once that is done, there's two things we can see whenever we go about and solve the dual of the subproblem. Either the subproblem is unbounded, meaning that the primal subproblem is infeasible, and meaning that we've just found an extreme array W for it. We saw that as well in lecture 6. Or it turns out that SDK has a solution that is finite with value ZK for that given X. Okay. So with this in mind, what I'm going to do is I'm going to revert back to my main problem and see if I can use that information. If it happens that we found SDK to be, so the dual of the subproblem to be unbounded, we can derive a feasibility condition to be imposed, which comes with the extreme array. That is, feasibility is only attained if this condition is observed. All right. So this is just telling us the following: as soon as you find an extreme array, you have to make sure that extreme array is bounded to an extent this can be yielding feasible solutions. So basically saying that X is kind of almost like a no-no, because for that X, this problem is, the dual is infeasible. Sorry, the dual is unbounded, meaning the primal is infeasible. So we revert back and generate this condition. Notice that this condition includes X for that array we just found. Otherwise, if ZK is finite, so the optimal must be on one extreme point of K. So what I can do is, if I do have all the extreme points associated with K, I just find ZK would be where that function here is attaining its maximum. So given a K, I look at the maximum of this function, which is basically this dual, and pick the best, which can conveniently be reformulated like this formulation has a few names. I can't remember what is the call. I've seen this called as a Minimax formulation. I think it's all called the epigraph formulation. Basically saying the following. So you have a collection of functions of this form. So pretend, just as a graphical representation, pretend you have for different i's, so I equals 1, I equals 2, I equals 3. And then suppose that this axis here is showing you the value of PK transpose EK minus CKX. And suppose that for I1 you are here, for I2 you are there, and for I3 you are there, and you want to pick the maximum of those. So basically what you do, you created this object theta, which kind of works like a ruler, like so. Actually, let me do this a single line, like so. And then what you do is you minimize this term until it hits one of the constraints. As soon as it hits one of the first of the values, so if it has to be above all the values, and we're minimizing. What it happens is as soon as it hit the largest of the one of them, it returns you that value. So notice that this problem, as it is, can be equivalently represented as a minimization of the single variable theta, where this theta is constrained to be above all of these elements for all extreme points. Okay, so all extreme rays have to be bounded, and I'm picking which is the extreme point that is leading me the optimum. This is, by the way, up to this point, the question that must be in your head is, why on earth are you doing that? So why is it so we're making this so complicated? Well, in the hypothetical, perhaps, unrealistic setting where we assume that we have all the extreme rays and extreme points, by doing so, we return or we recover a tractable formulation of our problem. So we went on having that dual level structure that we turned into a single level structure using the representation theorem, which gives us this setting. So now look what I have. I have a problem that is only dependent on x, doesn't depend on our y's. And the reason why it doesn't depend on the variables y anymore is that the y variables have been, or the subproblems have become implicitly represented by its extreme points and extreme rays. And I'll have for each subproblem k all its extreme points, for each subproblem k all its extreme rays. By the way, we know that this is the same as this. I think I changed it here just because I ran out of space in my slide, so I reverted to a more compact notation. But it means the same thing. Which is all nice and fun, but absolutely useless, right? Because when on earth you will have all the extreme points and extreme rays available to actually come up with this representation? Potentially never. But now we know that it turns out that we do know a technique that even though we don't know all of them, we can start to introduce them in a delayed fashion. Meaning that, okay, it's not that I know all of them, but I know how to generate them one by one as I generate solutions, and that perhaps can be put in an iterative process in a way that, because these terms, they only have to be above the maximum, it might be so that as soon as I found the correct set of extreme point where the optimal for this problem would lie, I'm done. So we can live, what we do is literally there's a bit of a hope in this, a hopeful or wishful process, because what we do is we hope that the process is such that we only need to generate some of those extreme points, and eventually we generate those correct ones where the optimal solution lies, and we can stop there without having to generate all of them. The same principle behind any cutting planes method, when you're just hoping that you just need to generate those cutting planes around where the optimal solution lives, and hoping that this is enough. Worst case scenario, you're gonna have to generate them all. So by using this sort of representation, you kind of have an implicit convergence proof. Pretty bad one, but it is. You worst case scenario, you generate all the extreme points and all extreme rays, and you will find your optimal solution. This is finite. Might take forever, but it is finite. Almost forever, but it's finite. So that's exactly what we're going to pursue. This is absolutely not practical formulation per se, but now we know, because we know the technique on how to efficiently generate extra variables and extra constraints, we can apply a delayed constraint generation strategy to deal with these constraints. I don't know why it's saying 6 and 8 here. It should be 9 and 10. So this is 9 and this should be 10. Okay. So basically generate those in a delayed fashion. How do you generate those in a delayed fashion? Well, you have to feed those that subproblem with solutions X. And for a solution X, you generate an extreme point or extreme ray. And then with a new found extreme point or extreme ray, you added this constraint. So this PR problem gets augmented with more of these, not all, but some of those. And then you solve it again and see if you get a new solution. And that new solution can be fed in the subproblem to generate new points and so on. And the only thing missing would be then figuring out when to stop. And that is basically what is behind the a Bender's decomposition approach. So we're gonna iteratively generate these cuts on this now called relaxed main problem that I now called in PM again, because that's actually the main problem we're going to be solving. It has this identification of iteration L, and basically what it's doing is solving a version of the previous problem PR with a subset of constraints. I just noticed that this should also say for all k in k equals 1 to capital K. Because you have those for each subproblem as well. There you go. Here we are. All right. Where this is a subset of the extreme points, and this is a subset of the extreme rays, the ones you found so far, and which are built with all the dual variables and extreme rays you found from your dual subproblem. Okay. So the question is to figure out how we go about with this. So for every time we solve the main problem for that iteration, we obtain a solution X, which is obtained after you considering a subset of constraints of these. We call them cuts. We call this an optimality cut because it's generated whenever you find an optimal solution for the subproblem, and we call this a feasibility cut because it's found whenever you found the dual to be unbounded, and therefore the dual subproblem to be unbounded, and therefore the primal subproblem to be infeasible. So that's a forcing feasibility. So you might see the terms optimality cut and feasibility cut. So notice that. So let this be the solution for the primal master, the main problem. Sorry, the main problem at iteration L. So once you found this solution, what we do is we go and look at our subproblem S with that X we just found and solve it for it. So that gives us Z of X bar of L. Okay. When this is the case, two things can happen, which would be akin to generating violated constraints that must be added to the main problem for the next iteration. So whenever we solve SLK, and that is feasible, you can find the dual value associated with this constraint. That would be PKIL, iteration L, That's an extreme point I. That's why I have it in here. And the K is because that's the subproblem K. Okay. So if you observe that this is the case, so from that you obtained when you solved the main problem, this is you just obtained when you solved the subproblem. If you observe this to be the case, what you will see is that in that picture that I drew, that you had that theta here and you that for I1, I, and you had different levels for the expression PK1 transpose EK minus C XEKX. So if that is violated, so basically what's happening is that you had your value theta set, say, here, and now you just found a new level there, which means that this theta would have to move up to capture the true maximum. So you found this violated constraint. If you found that this constraint is violated, then you just found something, you just found a point that has to be introduced and generate a new feasibility, optimality cut. And once again, if S is infeasible, then it means that you just found an extreme ray for which this happens, and therefore violating the constraint 10, which was this, well, originally this. Okay. So if you either observe this or you observe that, then you generate a new point that requires rinse and repeat. And here is a layout, a pseudocode for the Benders decomposition. So I'm calling here P and W the set of, not a set of indices of extreme rays and extreme points, but the actual set of extreme rays and actual set of extreme points. So this contains P1, P2 lowercase p's, and this contains W1, W2 lowercase as well. And we have one of those for each K and K. So perhaps we should even say that these are K and K to not cause confusion. Of course, they can be in the same set, but it's, important. Sometimes it makes sense to have this separation for subproblems. So what you do is you solve your main problem at iteration L, and you will obtain an X and a theta variable. The X is what you're going to feed in the subproblem, and the theta you're going to use to test for whether you found new information. And basically, for each of the subproblems, you can solve them feeding this solution. And notice that because this is in K, this could even be done in parallel. If you found X to be infeasible, then you capture that extreme ray and put it in the bag of extreme rays. Let me just put this just to remember that this is actually not a fix. It's just an optional thing. If you did find this to be feasible, then you found an extreme point and you added this to the bag of extreme points. And you're gonna carry on doing this until, so you repeat until you observe that the point you just found being that feasible, because if you found an extreme ray, then there's nothing you can do, you just go around. But until you found that your current theta value for that X, when you find the dual variable, this constraint is satisfied. Because this constraint being satisfied means that you found a solution for this problem. So you find an X and a theta such that this is satisfied for all extreme points. You didn't find a point for each that was violated. So if you satisfy for that extreme point, it satisfies, it's kind of like an umbrella sort of situation. You found the solution that represents the tip of the umbrella. So it holds for everything under that solution as well, because it is this extreme point where the optimal is. So there is no, the chasing for optimal solution stops There is nothing better around where you are. And because of convexity and so on and so forth, that means that this is an optimal solution overall. And then you return the x that you found and the theta values. And if you want, you can even keep track of your dual solutions, so you return the values of the y case as well. Of the solutions of your subproblem, so you can return the y's as well. So that's Bender's decomposition. Very, very straightforward as well. Well, not straightforward. Very simple to explain, very hard to implement in terms of efficiently having it implemented. So some interesting remarks. First of all, notice that whenever whenever you change your subproblem SK, truly is only the right hand side changing. So you can see from here that this is the term that is changing, right? So if you keep track of these subproblems, keep them somewhere where whenever you revisit, you're just changing the right hand side and optimizing again. It means that very often this is a very good candidate for dual simplex, because means that you have already a solution that is dual feasible and primal feasible, and then by changing the right hand side, typically you make it primal infeasible, but yes, still dual feasible. So there is implementation benefits, computational benefits from doing dual simplex in this sense. Of course, if that is the case, then the solution is optimal. So that's a way to test when to stop our algorithm. But another more common way is to use the notion of bounds, like we did with column generation. But here, the bounding is a bit more trivial, really. Recall that we are minimizing. So whenever you solve the main problem, you're getting a dual bound. Why is it a dual bound? Because the main problem is by definition a relaxation. Why is it in a relaxation? Because it just has some constraints missing. You don't have all the extreme points and extreme rates yet. And using the notion of relaxation we've seen in the course, this is simply a dual bound. Okay. Whenever you, if you need a primal upper bound, you can calculate that as well. And the way to do so is by simply looking at, so basically this would be a primal bound where you have a feasible x, you calculated the feasible y's for them when you solve the subproblem. So you can use that, but because you're getting different x's at every iteration, there is no guarantee that this thing is monotonic at all. I mean, you might be bouncing around bad or worse solutions as you go. So one practice we have is to keep this min here. So we are keeping the best upper bound we found so far. Remember, this is a minimization, so these are primal bounds, therefore upper bounds. So you just pick the smallest of them. And of course, it's not really hard to see that this value is exactly the objective function of the main problem, discounted the value of the theta variables, added the value of the objective functions of the subproblems. This is more useful because typically when we working with Bender's decomposition, and we might be dealing with, that was more of a thing of the past, but we might be with a solver that doesn't have a good interface to capture dual values from these constraints. Pardon me. Capture these dual values. So basically what we do is, and we're going to do that in our assignment as well, we work with the dual formulation of this problem and get the optimal variables from it, which will be the p's. So if you have a reliable interface, you can just solve the primal version of the subproblem and obtain the dual values associated with this constraint. But if you don't, for some reason, don't have an interface, an easy way to retrieve these dual variables, what you can do then is formulate the dual of this and then solve it as an optimization problem, which is what we're going to do for an assignment for just to practice. And also because that is a good idea, because then, there is some computational reasons to do so, and it is involved with the fact that when you write the dual of that subproblem, let me go back a few slides to show you that dual formulation. You can see that now you only change your objective function values, and that is somewhat easier to do than changing right-hand sides in constraint sets under a computational perspective. But anyway, that's more details that we're gonna play a little bit with in the assignment. Yeah, so and then you can use, of course, you can use this difference between lower and upper bound. It can be an absolute difference or can be a relative difference, a percentage of around the upper bound. You can use as a stopping criteria for your method as well. All right, this is all I had to say. The video is a bit long, so that's a good stopping point. So that finishes lecture 10. I hope this was informative. I know it's been quite a lot, but I wanted to make sure you get at least the idea behind these methods, so then you feel more confident to use them in your professional life from here onwards. So thank you for watching, and see you in the next lecture. Bye bye.